Welcome to the Deep Dive. Today we're plunging into the powerful and, let's be honest, sometimes uh, bewildering world of deep learning frameworks.
It can definitely feel that way.
Yeah, if you're an ML practitioner, a data scientist, or maybe a developer, you know this field moves incredibly fast.
Oh, absolutely. Lightning speed.
And navigating the sheer number of tools, especially the big players like Keras, TensorFlow, and PyTorch, well, it can feel a bit overwhelming, whether you're just starting out or maybe looking to switch gears.
That's exactly right. And our mission today really is to cut through that complexity.
Okay.
We're going to unpack the core ideas, the philosophies behind each of these frameworks. We'll show you how models are actually, created and operated.
Get practical.
Exactly. Provide some really practical comparisons. So the goal is for you listening to walk away feeling confident, really, about choosing the right tool for your next project.
Like a shortcut.
Think of it like that, yeah.
Yeah.
Your shortcut to truly understanding these essential deep learning partners.
All right, sounds good. Let's start then by unpacking that powerful partnership. Keras and TensorFlow.
Okay, so TensorFlow. It's an open source machine learning framework originally developed by Google.
Right.
It's primarily written in Python, and it's designed for building, well, everything from simple machine learning models right up to really complex deep learning applications.
And at its core, what's it doing?
At its heart, TensorFlow performs these intricate numerical computations using something called tensors,
Tensors. Okay.
which are essentially just multi-dimensional arrays of data. You can think of them like superpowered lists or grids of numbers.
So TensorFlow is handling the raw computational muscle, the heavy numerical lifting.
Precisely.
So where does Keras fit in? I hear that name constantly.
Yeah, you do. Keras acts is TensorFlow's official high-level API.
High-level API.
Got it. It was integrated directly into TensorFlow with a very clear purpose: to radically simplify the whole process of building and training neural networks.
Ah, okay. So that's where our engine and dashboard analogy really shines, isn't it?
It absolutely does. It's a great way to think about it. Imagine TensorFlow as this incredibly robust engine of a high-performance car.
Okay.
It's doing all the complex math, the operations on the numerical data, those tensors we mentioned.
Right.
Keras, then, is the user-friendly dashboard on that car.
Nice.
It makes this powerful engine accessible. It lets you drive and interact with it smoothly without needing to dive deep into all the low-level mechanics, the intricate wiring under the hood.
That makes perfect sense. So for someone maybe just starting out, or even an experienced person looking for speed,
Yeah, for rapid development.
what are the big advantages of using Keras with TensorFlow?
Well, one of the biggest benefits is just its sheer simplicity and the speed it offers for prototyping ideas.
Right. Faster iteration.
Exactly. Keras abstracts away. It hides a lot of the really intricate details, which means you can iterate on your model designs incredibly rapidly. And that speed of innovation it enables, whether you're a beginner or part of a small team, that can be a real game changer.
Okay. So when I'm actually building a deep learning model, what does that look like in Keras? How do I define its structure?
Building a model with Keras often involves stacking layers together, much like building blocks, really.
Okay.
You typically use something called tf.keras. Sequential. It's very intuitive because the data just flows from one layer straight into the next.
Sequential makes sense.
Yeah. And you'll frequently use layers that connect every neuron in one layer to every neuron in the next. Those are often called dense layers, fully connected.
Dense layers, right.
And for certain types of data, like images, you might need a layer that prepares your input first. For instance, transforming a grid of pixels, say 28 by 28, into one long continuous line of numbers, flattening it out.
Flattening, yeah. To feed into that first layer.
Exactly.
And how do you tell the model what kind of data to expect right at the beginning, the input?
Ah, good question. You do that by defining the input shape for the very first layer.
Input shape.
Yeah, this is a crucial step because it tells your model the exact format of the incoming data. So for example, if you're dealing with just a single numerical input for, say, a regression problem, you'd specify it expects just one feature.
Like one, maybe.
Exactly, like one. Or if it's an image, you'd define its height, width, and how many color channels it has, maybe like 28, 28, 1, for a grayscale image.
Got it. So the data is flowing through these layers. How does the network actually process it and learn complex patterns? Are there special functions involved?
Yes, absolutely. That's where activation functions come in.
Activation functions.
So these are nonlinear functions that introduce complexity. They allow the model to learn much more intricate relationships in your data than if it just performed simple linear calculations.
So they make it nonlinear.
Precisely. You'll see ReLU, ReLU, or rectified linear unit, used
Oh,
very commonly because it's computationally quite efficient. For binary classification problems like deciding between two options, yes or no, maybe cat or dog, you'd often use a sigmoid function in your final layer. That outputs a probability between 0 and 1.
sigmoid for binary.
Right. And for multi-class classification, where you're picking from many categories, softmax is your go-to function.
Softmax.
Yeah, it ensures your outputs are probabilities that all sum up to 1 across all the possible classes, so you know which class the model thinks is most likely.
Okay, so you've designed the architecture, picked the layers, the activation functions. What's the critical next step before you can actually start training it?
Right. The next crucial step is model compilation.
Compile.
Yeah, model.compile. This is where you essentially prepare the model for training by defining three key things: the loss function, the optimizer, and any metrics you want to track.
Loss optimizer metrics.
Okay. Think of the loss function as the model's report card. It tells you exactly how much it's messing up, how far off its predictions are.
How wrong it is.
Exactly. And just like you'd use different grading systems for different subjects, deep learning uses different loss functions depending on the task.
Okay.
For predicting numbers, like in regression, you might use mean absolute error, or MAE. For a simple yes-no question, that binary classification, binary cross-entropy, is common.
Binary cross entropy.
Yep. And for choosing from multiple categories, there are specific cross-entropy functions, like categorical cross-entropy or sparse categorical cross-entropy, depending on how your labels are formatted, whether they're one-hot encoded or just integers.
Got it. And the optimizer and metrics, what roles do they play?
So the optimizer, things like SGD or ADAM, that's the algorithm that actually adjusts the model's internal parameters, its weights, to try and minimize that loss function to get a better grade, basically.
It does the learning.
It drives the learning process, yeah. It nudges those parameters, usually after seeing small batches of data. And metrics, things like accuracy or maybe MAE again, are what you use to track your model's performance during training and evaluation. They give you human-readable insights into how well it's doing.
Okay, that makes sense. Then comes the real work, training the model.
Precisely. Training involves calling model.fit.
Fit.
You feed your data, your training data, to the model over multiple epochs. An epoch is one complete pass over your entire data set.
Okay, multiple passes.
Exactly. And it often processes the data in small groups or mini batches to make the training more efficient and stable.
Right.
After that intensive training, you need to assess your model using model.evaluate on data it hasn't seen before, like a test set or validation set.
Evaluate to see how it generalizes.
Exactly. This gives you an honest assessment of its performance, things like its test loss and accuracy. And finally, for practical use, you perform inference or prediction. Yeah, using the trained model on brand new data that it has never encountered, using it to classify images, generate text, whatever your task is.
That's a really clear workflow. Build, compile, fit, evaluate, predict. And once you put all that work in, trained a good model,
Yeah.
you definitely want to save it, right?
Oh, absolutely. You don't want to lose that. Keras provides model.save, which is incredibly convenient. It captures both your model's architecture, its blueprint, and all the learned internal parameters, the weights, typically saving them into a single file, often with an .h5 extension.
So everything's in one place.
Yep. This allows you to easily load it back later using model.loadModel and reuse your trained models maybe in a different application or perhaps for further fine-tuning down the line.
Very useful. So you've built this model, saved it. How do Keras and TensorFlow help apply these models in the real world? What are some common practical steps or use cases?
Well, a critical first step in almost all deep learning projects, something we shouldn't forget, is data preprocessing.
Right. Getting the data ready.
Exactly. For instance, if you have categorical variables like different types of fruit in your data set, you'll likely need to convert them into numerical representations the model can understand.
Like one-hot encoding.
Exactly, like one-hot encoding, where each category gets its own binary slot, like 1000 for apple, 0 for banana, and so on. This gets the data into the right numerical format.
Okay.
And for numerical features, normalizing them, maybe scaling them to be between 0 and 1, or standardizing them, can dramatically help your models converge much faster during training and often perform better, too.
So pre-processing is key for performance.
It's often an invisible but absolutely crucial part of any ML pipeline, especially with images or complex data.
Makes sense. And I've heard a lot about something called transfer learning. What is that, and how do Keras and TensorFlow help with it?
Transfer learning. It's a huge advantage in deep learning today. It involves taking a pre-trained model.
A model someone else already trained.
Exactly. A model that's already learned incredibly complex patterns on a massive data set. Think of models like VGG16 or ResNet, trained on millions of images from ImageNet.
Okay.
These models already understand fundamental visual features, edges, shapes, textures. So if you want to classify, say, cats and dogs, instead of training a huge network from scratch,
Which takes ages and tons of data.
right, you can take that pre-trained VGG16, maybe freeze most of its layers so their learned weights don't change.
Freeze them.
Yeah, lock them in place. And then you just replace and retrain its final output layer for your two specific classes, cat and dog.
So you adapt the end bit.
Exactly.
Yeah.
Or in natural language processing, you might take a pre-trained model like BERT or T5, which already understands language structure really well,
Yeah.
and you adapt it or fine-tune it for a specific task like sentiment analysis or maybe machine translation. This dramatically reduces the amount of data and training time you need.
Wow.
It makes really advanced AI much more accessible, even if you don't have Google-level resources.
That's incredibly powerful. Okay, so Keras and TensorFlow together offer this really user-friendly but powerful way to do deep learning, including advanced stuff like transfer learning. But now let's bring in the other big name, PyTorch. How does it compare?
Right, PyTorch. It's the other major player. It's also an open source machine learning framework widely used for deep learning, but this one was developed primarily by Meta AI, Facebook's AI research lab.
Okay, Meta AI.
And while both frameworks are incredibly powerful and can achieve similar results now, they historically approached a core concept quite differently: how they handle computational graphs.
Computational graphs. Okay, can you quickly break that down? What does that mean in this context?
Sure. So in deep learning, when you define a model, you're essentially setting up a sequence of mathematical operations that process your data. Think inputs, layers, doing calculations, outputs.
The flow of computation.
Exactly.
Yeah.
A computational graph is just a way to represent these operations and how the data flows through them. Now, historically, TensorFlow used what's called a static graph approach,
Static graph?
often called define then run. This meant you had to define the entire computational graph up front, build the whole blueprint, essentially before you could execute any operations or feed any data through it.
Define everything first, then run it.
Right. Now, this had advantages. It was potentially beneficial for large-scale optimization and deployment because the whole structure was known in advance, but it could make debugging more challenging because you couldn't easily inspect intermediate values during the execution. If something went wrong deep inside, figuring out where was trickier. It was sometimes described as trying to fix a car engine with the hood welded shut. You couldn't easily see what was going on inside step by step.
Okay, yeah, I can see how that might be a headache, especially during development or research.
It definitely could be. PyTorch, on the other hand, gained a lot of popularity, especially early on, because of its dynamic graph approach,
Dynamic graph.
also called define by run. With PyTorch, the computational graph is constructed on the fly as the operations are actually executed.
As you go.
Exactly. As your Python code runs, the graph gets built. This offered much greater flexibility. It made debugging significantly easier because you could use standard Python debuggers and inspect values at literally any point in the process.
Like pausing and checking things mid-calculation.
Precisely. And it also allowed for more dynamic adaptive model architectures models whose structure could change based on the input data during runtime. This flexibility really appealed strongly to researchers exploring new ideas.
That sounds like a pretty significant difference, especially for researchers wanting to experiment quickly.
It was a major differentiator, yeah. Being able to see inside the model so easily was a game changer for rapid experimentation and, pushing the boundaries of AI.
But I've heard, like you hinted, the lines have blurred a bit recently. Is that static versus dynamic distinctions still as crucial today?
That's a really important point. The lines have blurred considerably. It's quite fascinating, actually. TensorFlow 2.x, starting a few years ago, introduced and enabled by default something called eager execution,
Eager execution.
which essentially adopted a define-by-run paradigm very much like PyTorch.
So TensorFlow changed to be more like PyTorch in that way.
Largely, yes. In eager execution mode, TensorFlow operations execute immediately. They don't just build a graph node. This makes development and debugging feel much more interactive and Pythonic, similar to PyTorch.
Interesting.
So while they started with very different philosophies on graph execution, they've converged quite a bit on this front. Now, Both offer a lot of flexibility in how graphs are executed day to day. The old static versus dynamic debate is much less pronounced than it used to be.
Okay, so if they're both somewhat defined by run in practice now,
Yeah.
what about ease of use and the learning curve? We talked about Keras being super friendly. How does PyTorch compare there?
Right. Keras, as TensorFlow's high-level API, definitely remains incredibly user-friendly. It excels at rapid prototyping, and it's often seen as perfect for beginners who really prioritize simplicity and getting something working quickly.
Straightforward.
Very. PyTorch, however, is often praised for its intuitive Pythonic feel.
Pythonic. What does that mean exactly?
It means that for people already comfortable with Python programming, PyTorch's syntax and structure often feel very natural, like an extension of standard Python, rather than a separate domain-specific language. You manipulate tensors much like you'd manipulate NumPy arrays, for example.
Okay, so it feels familiar to Python developers.
Exactly. And PyTorch handles things like automatic gradient calculation very cleanly, which simplifies the backpropagation process compared to, say, trying to implement it manually in NumPy. It also maintains a very consistent standard training loop structure.
It's a training loop.
Yeah, the typical steps. You clear the gradients from the previous step, you run your data forward through the model, the forward pass, you calculate the loss, you compute the gradients using backpropagation, and then you tell the optimizer to take a step to update the model's weights. This clear, consistent structure is very appealing to many developers and researchers.
So Keras offers simplicity via abstraction. PyTorch offers simplicity via feeling like natural Python. Interesting trade-off.
Kind of, yeah. Different flavors of user-friendliness.
What about when you need more control? When you need to really get into the nitty-gritty, maybe build a completely novel type of layer or operation?
That's where flexibility and control become really important. And generally, PyTorch is often seen as offering more direct, fine-grained control over low-level operations.
Or direct control?
Yeah, you work directly with PyTorch tensors, which, as I said, behave very similarly to standard Python arrays or NumPy arrays. This makes it a favorite for researchers who are really pushing the boundaries, who need to create highly custom network layers or implement complex mathematical operations that might not be available out of the box in a higher level API.
So it gives you the keys to the lower levels more readily.
Kind of, yeah. It makes fewer assumptions, perhaps. Now, that being said, while Keras offers high-level abstraction, it's important to remember that it's built on top of TensorFlow. So TensorFlow itself still provides access to its lower-level APIs. If you need to, you can absolutely drop down from Keras and use TensorFlow core operations for more granular control when a specific intricate need arises. It's possible, just maybe less common or direct than in PyTorch.
Okay, so if you're doing cutting-edge research, PyTorch might give you that low-level flexibility more easily, but TensorFlow still allows for customization if you dig a bit deeper.
That's a fair summary, I think.
How about getting these models out into the real world? Production deployment. That's crucial for businesses.
Hugely important. And this is an area where TensorFlow has historically had a very strong advantage due to its mature and comprehensive ecosystem for production deployment.
Okay, what does that ecosystem include?
It includes really robust production-ready tools like TensorFlow Serving, which is specifically designed for deploying trained models in high-performance production environments.
TensorFlow Serving.
There's also TensorFlow Lite, which is optimized for deploying models on mobile devices, embedded systems, and edge devices, think smartphones or IoT gadgets. TensorFlow Lite for the edge.
Exactly. And then there's TensorFlow Extended, or TFX.
TFX.
TFX provides a whole platform for managing end-to-end machine learning workflows. This is a critical part of MLOps machine learning operations, ensuring that models are built, tested, deployed, monitored, and retrained reliably and repeatably in production.
So a full MLOps pipeline tool.
Yes. This very robust suite of tools has made TensorFlow a very strong choice for large-scale industry adoption and complex production systems.
Okay, that sounds quite comprehensive. And PyTorch, has it caught up in that regard, or does TensorFlow still hold the edge for deployment?
PyTorch's production story has definitely evolved significantly. Its capabilities, like TorchScript.
TorchScript.
Yeah, TorchScript allows you to compile your PyTorch models into a statically typed graph representation that can be optimized and serialized for deployment in environments where Python might not be ideal, like C++ runtimes.
Ah, okay, for
Yeah.
optimization and portability.
Exactly. And there's also TorchServe, which is their tool for model serving, similar in goal to TensorFlow Serving.
These tools have matured a lot and are continuously improving. So while TensorFlow's ecosystem was historically considered more extensive and battle-tested for production, that gap has narrowed considerably. PyTorch is increasingly viable and used for many production use cases today.
So the gap is closing there too. Interesting.
Definitely.
What about the communities around them? Who's using what, and where do people go for help or discussion?
Right, community is huge. TensorFlow, being backed by Google and having been around longer in its modern form, generally boasts a larger and perhaps more established community overall.
Bigger user base.
Probably, yeah. It has incredibly extensive official documentation, countless tutorials, blog posts, courses, and very widespread adoption across various industries. You'll find TensorFlow used a lot in large tech companies and enterprise settings.
Okay, and PyTorch?
PyTorch, supported by Meta AI, has experienced incredibly rapid growth and gained immense popularity, especially within the research and academic communities.
More focus on research.
Historically, yes, its flexibility really resonated there. It fosters a very active and helpful online discussion forum, and there's a wealth of community-contributed code, models, and resources available, alongside its own comprehensive official documentation. You see it heavily used in AI research papers, for instance.
So TensorFlow, maybe stronger roots in industry, PyTorch, stronger roots in academia and research, but both are widely used now.
That's a reasonable generalization, though the lines are blurring there too. You see PyTorch in industry and TensorFlow in research, of course.
Okay, and finally, the question everyone always wants to know. Performance. Which one is faster? Is there a clear winner in terms of raw speed or efficiency?
Ah, the speed question. The reality is, for many common deep learning tasks today, both frameworks are highly optimized for performance and scalability.
Both are fast.
Both are very fast, especially when you leverage hardware accelerators like GPUs or TPUs. PyTorch, for example, makes it really straightforward to move your models and data tensors to a CUDA-enabled GPU to get massive speedups.
Easy GPU usage.
Very easy. And TensorFlow has similar capabilities, especially with its tight integration with Google's TPUs as well. Recent advancements in both frameworks, their underlying libraries like cuDNN and compiler technologies, mean that for most real-world scenarios, both can achieve comparable top-tier performance.
So it's usually not the deciding factor.
Often, the performance difference on standard tasks isn't significant enough to be the primary reason to choose one over the other. The choice usually comes down more to the factors we've just discussed: the ease of use for your style, the flexibility you need, the specific ecosystem tools you require for deployment, and maybe just personal or team preference.
Okay, that's really helpful. We've covered a lot of ground today comparing these frameworks across different dimensions. So the big question remains, how do you, the listener, choose your deep learning partner? Is there a single best one everyone should just use?
No, absolutely not. I really want to emphasize that. Neither framework is definitively better across the board.
No silver bullet.
Exactly. The optimal choice truly depends on your specific needs, your project goals, the context you're working in, and frankly, your personal or your team's preferences and existing skills. It's all about finding the right tool for your specific job.
Okay, so if someone listening right now is thinking about their next project, trying to decide, when would you suggest leaning towards Keras and TensorFlow?
I'd say lean towards Keras with TensorFlow if your top priority is rapid prototyping and just overall ease of use, especially for maybe more general machine learning tasks or standard deep learning architectures.
Get started quickly.
Get started quickly, iterate fast. It's also often a strong choice when robust production deployment is a critical requirement from the outset, particularly if you're targeting mobile or edge devices using TensorFlow Lite, or if you need to integrate tightly with established MLOps pipelines like TFX.
Especially on Google Cloud.
Yeah, and especially if you're already deeply embedded in the Google Cloud ecosystem, TensorFlow often offers a very seamless integration path.
Makes sense. And what about PyTorch? When does that really shine as the potential choice?
PyTorch is often the preferred choice if you're primarily involved in deep learning research.
Research focus.
Yeah, because it generally offers that maximum flexibility, the dynamic graph manipulation we talked about. Even though TF is eager now, the feel is still there, and that direct control over network layers and operations, which is key for exploring novel ideas.
Right.
Also, if you strongly prefer that Pythonic coding style, if you want something that feels deeply integrated with standard Python programming, PyTorch often feels more natural to many Python developers.
Feels like home for Python folks.
Can do, yeah. It's also become a very strong contender, arguably the leader in some areas, for advanced natural language processing, NLP, and generative AI applications.
NLP and GenAI.
Yes, partly thanks to fantastic libraries like Hugging Face Transformers, which integrates extremely well with PyTorch for tasks like text classification, machine translation, using models like BERT, GPT, T5, and so on.
Hugging Face is huge there.
Absolutely. And maybe also if you're working with highly custom data sets or need to implement very sophisticated data augmentation techniques, PyTorch's flexibility in data loading and transformation pipelines, like using TorchVision.transforms, is often praised.
Okay, so research, Pythonic feel, NLP Gen AI, custom data work, lean PyTorch, rapid prototyping, production, mobile edge, MLOps, Google Cloud, lean, TensorFlow, Keras.
That's a pretty good summary of the common leanings, yeah. But again, with caveats, the lines are blurring.
Right, and it sounds like they're both evolving and sometimes even adopting features or ideas from each other. What does the future hold for this landscape? Are they just going to merge into one thing eventually?
Haha, probably not merge entirely, but the future definitely points towards continued convergence in many ways.
Convergence.
A prime example of this is Keras 3. This is a major recent development. Keras 3 has this remarkable ability to run on multiple backends.
Multiple backends, meaning?
Meaning you can write your Keras code once and choose to run it using TensorFlow or PyTorch or even JAX as the underlying computation engine.
Wow, write once, run anywhere. Almost.
Kind of. It's a big step in that direction. This development strongly suggests that the distinctions between the specific framework APIs might continue to blur. It potentially makes the high-level interface more important than the specific engine underneath for many users.
So the focus shifts.
It could shift even more towards understanding the core deep learning concepts, layers, activations, loss functions, training loops, rather than being rigidly tied to the specific syntax of one tool. Keras 3 aims to abstract that away further.
That's fascinating. So with that potential future in mind, what's your final piece of advice for our listener trying to navigate all this today?
I think the most powerful approach, if you have the time and inclination, is actually to gain some familiarity with both.
Learn both.
At least the basics. Learning how to implement a simple model in both Keras with TensorFlow and PyTorch will give you immense versatility. It deepens your understanding of the underlying concepts because you see how different tools express them.
See from different angles.
Exactly. And it makes you much more adaptable as the field continues to evolve. But most importantly, experimentation is key.
Get your hands dirty.
Yes. Try building something, even a small project, in both frameworks. See which one feels better for your workflow, which one clicks for the way you think about problems. Find what truly works for you and the specific challenges you're trying to solve. Don't just read about it, do it.
Excellent advice. Well, that's our deep dive for today. We've navigated the really powerful capabilities of Keras, TensorFlow, and PyTorch. We explored everything from their core philosophies, static versus dynamic graphs, eager execution, all the way to their practical applications in building, training, evaluating, and deploying models.
Yeah, we've seen how these frameworks empower incredible tasks.
Huh?
Things like image recognition from classifying simple handwritten digits like MNIST right up to complex real-world problems like telling cats from dogs.
Right.
They drive natural language processing, enabling things like text classification, sentiment analysis, machine translation. And they even powered the really intricate world of deep reinforcement learning, which has led to superhuman performance in complex games like chess and Go.
It's amazing stuff. So
Wow.
now that you listening have this blueprint, this map of the landscape, the real learning, as we just said, begins with hands-on experimentation.
Absolutely.
Try building a model, maybe a simple image classifier or a basic regression model in both frameworks. Really feel the differences and the similarities firsthand. Pick a small project, get your hands dirty with the code, and see which one resonates more with you.
And it's worth remembering, despite the incredible strides we've made with deep learning, these models and frameworks still face really intriguing challenges. There's still so much work to do.
Like what?
Well, things like ensuring you have high-quality, unbiased data. Managing the immense computational demands, you often need powerful, expensive GPUs for training large models. Understanding why a model makes a certain prediction, that's model interpretability, and guarding against things like adversarial attacks, tiny deceptive changes to input data designed to deliberately fool the model.
Lots of open problems still.
Definitely. But your deepened understanding of these foundational frameworks, Keras, TensorFlow, PyTorch, positions you not just as a user applying existing tools. it potentially positions you as a contributor, someone who can help tackle these open problems, push the boundaries, and really help shape the very future of AI.
A fantastic thought to end on. Thank you for that deep dive.
My pleasure. It was great discussing it.